Hello, good morning, or I should say good evening, where I am right now. Anyway, I'm Bhavani from the University of Texas at Dallas, and I'm very honored to give this keynote presentation at IEEE ICKG, which is a top conference. And so I'm really pleased to be here, although I'm sorry I cannot be there in person. So I'm giving this talk virtually, but hopefully next year we can all be together at IEEE ICKG. So this recording is made on Thursday, August 6th, 2020, and my keynote presentation is going to be on August 11th, 2020. And again, thank you very much. So I'm going to share my screen. Okay. Great. So the title of my talk, Cybersecurity Meets Big Knowledge. And what I'd like to talk about is developing a secure Haze theorem. And I'll talk about Haze. It was a brilliant idea and research and effort by Dr. Jingdong Wu, who is, I believe, one of the founders of this conference, and he's done some really great work. And so what I'm going to talk about is how can we make Haze secure? So the outline, first I will discuss Haze theorem very briefly because it's given in IEEE Transactions on Knowledge and Data Engineering, paper published by Professor Jingdong Wu and his team, and then talk about how we can develop a secure Haze theorem. So big knowledge, security, and privacy, a number of topics. Privacy aware, policy-based big knowledge for security applications, attacks to big knowledge, and then something that's very close to my heart. A lot of my research has been in this area, and that's on inference problem and assured knowledge sharing. So these are all aspects I believe must be investigated, plus many more topics, but I'm only talking about the key topics and those topics that I've conducted some research on, to developing a secure Haze theorem. And then I'm going to give some idea how we can apply to some real world applications. And so one of the areas I'm focusing on is the Internet of Transportation and Infrastructures. In particular, it comes under cyber physical systems. And finally, conclusion. So our research has been funded by a number of agencies and organizations in the United States. And I also like to thank several of my colleagues, including Professors Alvaro Cardenas, he is an expert in cyber physical systems and security, and Murad Kantajulu, who is an expert in adversarial machine learning, Latifa Khan, who is an expert in applying data science for cybersecurity applications, our PhD student who just completed, Dr. Raul Quinones, who is supervised mainly by Dr. Alvaro Cardenas, but I'm his co-advisor. And also many of you all who attended ICDM 2013, it was in Dallas, Texas. It was, remember, during that snowstorm, it was not snow, ice storm. That was in December 2013. And the person who organized it for us was Ms. Rhonda Walls, and she's our project coordinator. Okay, so part one is Haze theorem. So Professor Jingdong Wu and his colleagues published a landmark paper in IEEE Transactions on Knowledge and Data Engineering, and that was back in 2014. And they developed this whole concept called Haze. So we know that collection, storage, access, manipulation, mining of massive amounts of data have resulted in the design and development of big data management and analytics. Right? So we call it BDMA technologies. Subsequently, in 2014, the Haze Theorem has emerged as a way to characterize big data. So, as discussed by Xingdong Wu and his colleagues, big data starts with, we know, large volume, heterogeneous, H in the Haze, autonomous, A for Haze, with distributed decentralized control, C in Haze, and seeks to explore complex evolving, E in Haze, relationships among data. So we know that's large amounts of data, it's autonomous sources, it's distributed and decentralized, and its relationships are complex and evolving. And over the years, the last 5-6 years, I believe that Haze theorem has become fundamental to big data characterization. Just like Newton's laws are to physics. We know what Newton's laws are, right? They were, I believe, developed in what, 1600 something. And so almost 400 years later, now we have big data, and Haze theorem is fundamental to big data. Associated with Haze is the big data processing framework, and I'll talk about the framework in the next chart. It consists of 3 tiers focusing on data access, data sharing, data mining, analytics, right? So there's also some additional areas that we have been focusing for our work on data privacy. I'll talk about it later. And that is on data collection as well, collection, storage, management. So it's all under data access here. Okay, so the big data processing framework deals with heterogeneous, autonomous, complex, and evolving data, right? Because we have lots and lots of data, we are forming relationships, and that has resulted in big knowledge, right? So we extract all the information from the data, that is information, data with context, and then when you put some common sense into it, then you get big knowledge that deals with, and as mentioned in the paper by Dr. Wu and others, fragmented knowledge from heterogeneous autonomous information sources for complex and evolving relationships in addition to the domain expertise. That's what gives you knowledge, right? You put some sense into it and you bring the domain expert to make it convert data to information to knowledge. Okay, so for details on Haze and the big data processing framework, I'm going to refer to the paper by Dr. Xingdong Wu and his colleagues. So continuing, the Haze theorem, the big data processing framework, remember, that is at the heart of the Haze theorem. And so I've duplicated the figure from Xingdong and his team's paper on Haze. So it's sort of a cycle, a life cycle, right? You have information sharing and data privacy, local learning, and then you learn at the local level, you develop the model and then fuse all the models, mining from sparse, uncertain, and incomplete data. So you've got to fill in all the blanks, what happens, and then mining complex and dynamic, evolving data, right? So that's at the outer, complex, dynamic, and evolving data. You learn, local learning and model fusion, and then you've got sparse, uncertain data, and then you have information sharing and data privacy. Yes, when you share information, and I'm going to talk quite a bit on data privacy. And of course, big data applications and knowledge. And one such application I'm going to talk about here is the Internet of Transportation. And at the heart of all this is the big data mining platform. So that is the big data processing framework that the inventors of Haze came up with. And that's Dr. Xingdong Wu and his colleagues. Okay, so that is part 1. Now, from Haze, how do we move to Secure Haze? So, Secure Haze, I believe, I took that picture from Dr. Wu's paper towards Secure Haze. So, how can we develop a secure big data processing framework, right? This is the total picture. So you have, remember I explained earlier what this big data processing framework is, but security and privacy, not just privacy, security as well. You've got to prevent all the attacks that are happening on the various stages, various activities, and ensure the privacy, because you are collecting lots and lots of data, and it's going to impact all of the activities in the cycle, right? So that would include mining from sparse, uncertain, and incomplete data. Then you mining complex and dynamic data. From there you learn local learning, and then you develop models and fuse all the models. And then in the inner circle, you've got extract all the information, you share it, and then you have to ensure privacy, and then big data applications and knowledge, such as Internet of Transportation. But then every step of the way, you've got to be concerned about security and privacy, right? Because every activity, what happens if your machine learning techniques and the data science techniques are attacked, right? So that's going to be, then you cannot rely on any of the results. So those are some of the things that I'm going to talk about. And so I'm not going to provide a complete solution to Haze from security point of view. A lot of work has to be done. So I'm going to talk about the various building blocks. Sorry, and eventually all these building blocks have to be put together. Okay, so just as a side note, I've got 1 hour for the talk. So hopefully I'm going to talk for about, I don't know, 50 minutes. And hopefully we can have some questions and answers after that. And I will be present for the keynote address. So I'll be there to answer questions, presence virtually. Okay, continuing with Secure Haze, what are some of the key aspects? How do we develop a secure version of the Haze Theorem? When I say secure, security and privacy. The key characteristics of Haze should include security, privacy, whether we are dealing with heterogeneous and diverse data types, autonomous distributed control, and complex and evolving relationships. Security and privacy play a very important role in Secure Haze. When massive amounts of data are collected, how do you ensure the privacy of the individual, especially when the data may be heterogeneous, images, text, and video, and the relationships between the data may be evolving? One could put together data stored in clusters of machines. Remember, it's all distributed. And you can extract information from the data, and together with the expert, you can convert information into knowledge. But then there could be so much knowledge, and that's why we call it big knowledge, and infer something that could be highly private, right? When you put collections of pieces of public data together, you could have private, or collections of unclassified data together, and you could get top secret. That's very dear to me because that's the inference problem, and I've done work in this area since 1985, so about 35 years. The individual machines in the cluster may be attacked, and as a result, the entire system may be compromised, right? So when I say individual machines, because remember, one of the key premises of Haze, it's distributed. And so when you have a distributed set of nodes, right, the algorithms in one of the nodes, the machine learning algorithm in one of the nodes could be attacked. As a result, the whole system could be compromised. Security and privacy also impact the big data processing framework. That's what I mentioned in the last chart. The data mining results could be highly private or sensitive. When data is shared between individuals, you can leak sensitive information, right? So that's quite scary. And you can also reason under uncertainty. There's missing data could result in serious integrity violations, right? So big knowledge, security, and privacy, essentially they are at the heart of Secure Haze. And so I'm going to talk about what are some of the building blocks to achieving security and privacy for big knowledge. As a result, security and privacy for big data processing framework, and as a result, we get Secure Haze. Okay, so big knowledge, security, and privacy. So very briefly, there are technological advances, right, and novel applications, such as, I'm going to talk about Internet of Transportation. It is possible to capture, process, analyze large amounts of data for security tasks. So it's not only for security tasks, large amounts of data for healthcare, for finance, and for, for epidemiology, such as COVID-19 that we are being faced with today, and autonomous vehicles, you name it, right? So there is lots and lots of data to be captured, but the analytics can also be applied to cybersecurity tasks such as intrusion detection, insider threat detection. So anyway, such tasks include like authentication, access control, anomaly detection, user monitoring, protection from insider threat, malware analysis. Okay, so by analyzing and integrating data collected on the web, one can identify connections and relationships among individuals. And that could in turn help us with homeland protection and disease outbreaks, like that's what we are being faced with, right, today. So collected data, even if anonymized, right? So you collect lots of data, but you can anonymize, but then you can link the anonymized data together and be able to infer something that's highly private, right? So for example, at University of Texas at Dallas, right, we have 7 female professors and 50, probably altogether 50. So let's say 40 something male professors, okay? So, sorry, this is, okay, 40 something male professors. And so, so what happens is that when this happens, right? So how can you sort of identify an individual professor, right? So you don't give out the name of the individual professor. What you can say is that, you know, it's going to be one of the female professors. So there are only 7 female professors. And then in another piece of information, you can say the professor is an IEEE and ACM fellow. And then there's only one person, a female who is an IEEE and ACM fellow, or even just IEEE fellow. That's just myself. So you can put pieces together and be able to infer something that is highly sensitive, okay? So security tasks such as user authentication, access control may require detailed information about users, even to do multi-factor authentication. This information, if misused or stolen, can lead to privacy breaches, right? Over time, together with reasoning techniques and analytics, the data is converted into information and knowledge. So one such representation for knowledge we know is knowledge graphs, right? They have roots in semantic web for information, representing information like RDF, and the machine learning world and the AI world, artificial intelligence, such as semantic nets and conceptual graphs, right? Combined with the semantic web technologies all together, now we have these knowledge graphs. That's just one such representation. So the directions include securing the knowledge, privacy enhanced techniques, big knowledge for cybersecurity, and attacks to big knowledge. So these are some of the topics that I'm going to discuss over the next few charts, where I'm keeping an eye on the time. So I think I have talked for about 18, 19 minutes. Okay. So what is our motivation for privacy? Remember I said as a result of data mining. So I use the words data mining, machine learning, data science, sort of interchangeably, but yes, there are some differences. So data mining, security, and privacy, I introduced at the IEEE 11.3 in 1996 in Como, Italy. So it's not just myself. I was a joint work between myself, Chris Clifton, and Don Marks. So Chris and Don presented some of the work at ACM Sigmod workshop that same year. And I gave a keynote in Como, Italy, and later at PAKDD in 1998. And I believe it was Dr. Xingdong Wu who invited me to give that keynote address at PAKDD in Melbourne, Australia. So I talked about data mining, security, and privacy, and subsequently published, I call it a landmark paper, I'll tell you why, at NSF in 2002 that spawned a new area of research. I call it a landmark paper because I was the program director at NSF in 2002 when I published this paper in SIG-KDD, that's the magazine, Explorations for Knowledge Discovery and Databases. And so when you're a program director at NSF and then you publish a paper, right, that can spawn a new area of research. And so everyone is interested, it gets citations, so I call it a landmark paper. Similarly, I would definitely call Dr. Xingdong Wu's Haze paper a huge landmark paper, okay? And if you look at the citations, it occurs, I think, thousands of citations. And that's one of the reasons I got very interested in looking at secure haze. Okay, so privacy preserving data mining, you have original data, you add some noise, and then you get X prime is noise added data, and then you modify the data mining process, right? And you have the final modified result. But the final result should not deviate from the original result that you would have gotten. Otherwise, what's the point in doing data mining if you're going to get garbage results? So the challenge is to modify the data in such a way that the end result is going to be the same. So when I joined UT Dallas, so I've had a 35-year career in data security and privacy and data science. Started at Honeywell in 1985. It used to be called data management and computer security. But of course, now it's cybersecurity and data science. And then from Honeywell, I was at the MITRE Corporation in Massachusetts for several years. And then I was at National Science Foundation, joined UT Dallas in October 2004. And so myself and Dr. Murad Kantarjulu, who happens to be Dr. Chris Clifton's student, Dr. Li Liu, she focused on privacy preserving decision trees and the perturbation method, right, in the mid 2000s. So now we have big data and the Haze Theorem. So data mining, security, and privacy is exacerbated with big data and data science. So I hosted an NSF workshop on big data security and privacy in September 2014, and we presented the results to Interagency Working Group in February 2015, and some efforts on data privacy, big data privacy was funded by various agencies since then. So here are some of the papers that I referenced. Okay, so now let's go more seriously into privacy. Lots and lots of data being collected, right? Because you've got what's this? Your blood pressure monitoring, or diabetes monitoring information, your Fitbits. So mobile devices, all we need is the smartphone, right? They have become prevalent computing platform. It's got billions of users. And there is a movement now among psychologists, sociologists called quantified self. And the whole idea is to gather lots of information about a person and then analyze the information. So it's big data analytics. Why? Because remember I said, so many good things can happen, right? Like United Nations now has an initiative called AI for Good. And so looking at applying AI for the good of humanity, right? So you gather all this information and then you decide, you can give targeted treatment to individuals. So that's really a great thing, right? Data is being shared by service providers, retailers, and as a result, you can give some good advice to people about their health, about spread of diseases. So some very good things can happen. But at the same time, there could also be some very bad things that could happen because such data collection and sharing are often being carried out without the user's knowledge. And so there's a grave danger. So very bad things can happen for personal data, and it can be used for improper purposes. For example, data collected by a device monitoring blood glucose levels, right, that's here. It might be used by an insurance company not only to deny coverage to myself, assuming I've got diabetes. It could also deny coverage to my son and my grandchildren, right? So that's going to be a big problem. Such privacy violations could easily get out of control, right? If the data collected could aggregate financial and health related data with tweets, Facebook activities, and so on. So it could result in lawsuits against data collectors and psychological and physical distress. So to address these growing challenges, we need tools and techniques, what we call privacy protection in these quantified self applications. So how do we do it? We have come up with an approach for privacy aware quantified self. We call it, it could be a big knowledge framework. This is one key element, I believe, of secure haze, right? So it's sort of building blocks, right, that you have to put together. So what we are saying is all of the health related fitness data, location, social media, image, video, all of the data is coming in. You collect data, you store and access the data, you analyze the data, data mining, and you share the data. And some of the data encrypted in the cloud storage, you can provide cloud-based services, querying and updating the data. We call this privacy-aware quantified self-manager running on a mobile device. So we have introduced one more layer, that is data collection, but we can incorporate collection, storage, and access as part of one layer, because Haze talks about data access, data analytics, data sharing, right? So we have sort of extended it, but we can combine it. But the main idea is that policies should guide this entire process. So remember the big data processing framework of Dr. Xingdong Wu? All of the activities, policy should guide, and that's what our premise is. Policy aware, big knowledge, data collection, storage, management, sharing, and analytics, okay? So as I said, more and more data collected, storage on the device will not be sufficient to allow all of the data. So we, as I said, some of the data is in the cloud, access through some services, but you can have some access control policies, local apps running on your mobile device, to give some access to the data. So some information is going to be in the mobile device. When needed, these applications will be allowed to access some of the encrypted data stored in the cloud through some query interface. So for instance, you know, a 20-year-old, right? You don't have to take her or his maybe blood sugar every day if he doesn't have diabetes and if he's not or she's not overweight. You don't have to weigh him or her. But a 60, 70, 80-year-old, it's different, right? You'll have to weigh him or her and collect the blood pressure, especially and blood sugar, if there are some pre-existing conditions. So anyway, you don't have to gather too much. That way you can sort of limit the amount of data collected. In other cases, you may also have to delete data, right? What happens when you delete data? What are the policies, right? Is a cloud service provider going to keep the data? So we envision that data sharing and analytics will be carried out using the services running in the cloud. So based on different scenarios, some of the data could be sent without any modification, like heart rate, and some others, right? You may want to modify, perturb, and so on, and send it to the cloud. So again, the key point is that policies have to guide, right? Your cloud-based platform. This is the privacy-aware quantified self, you know, local data store, data access framework, and mobile applications. So the main point is, what are these policies? Now, we computer scientists come up with some TOY policies. So we say, okay, I will tell you a secret, but don't tell that secret to John. But that's not the way in the real world. Real world policies are very, very complex. And so we have started a project with a top policy expert. She's the dean, Jennifer Holmes. She's the dean of our school, economics, policy, and political sciences. So my colleague Alvaro Cardenas and Jennifer Holmes, they have a joint project from NSF where they are looking at the policies for the power grid in the country Colombia. That is the South American country Colombia. So they are looking at policy-aware power grids, right? Securing and privacy of the power grids. So they're coming up with some realistic policies. Okay, so now that we have finished the privacy aware, now I'm going to talk about another aspect that we need to handle for Secure Haze, and that is big knowledge for cybersecurity applications. This is joint work with Latifa Khan, as well as you may all have heard of him, Professor J.W. Hahn from University of Illinois. So we look at all of the past knowledge, right? Data converted to information, converted to knowledge to build the classification models. And we predict the labels of the future instances using the model, and it can help with this decision making. Okay, so what are big knowledge streams? Continuous flow of knowledge, right? Data converted to information, converted to knowledge. Very common in our connected world, massive amounts of knowledge. So all of the information is coming, or knowledge. We have classification models, but these are not static models, because remember, evolving knowledge and relationships. So as things evolve, right, the models are going to change. And so time to time, the models are updated. And then you have test traffic comes in, and then the models will decide, okay, is it attacks or not? If it's benign, it goes to some server. So the thing here is that we develop, and this is some invention in this paper here, ensemble of models, a collection of models. And we have presented quite a few of these papers in IEEE ICDM. So ensemble of models, and these models are continuously updated. So sometimes the models may not be valid at some point, and so we throw away and replace it with some new models, right? So some old models may still be valid, but some new models or even old models sometimes may not be valid. So we throw away the models and use the models that are valid and develop new models. So something that is very interesting here also, we develop something called novel classes, novel class detection. So it doesn't have to be a red class or a blue class. We can have some really novel class, which is purple class, right? So that's something that could help us perhaps with zero-day attacks. We haven't tested our algorithms. We tested our algorithms for, it was funded by NASA for faulty reports in spacecraft, but we haven't done that yet for cybersecurity. But that's something that we believe, because we don't have lots of cybersecurity data, so we can apply to detect new viruses and malware, because that could go into the novel class. Okay, so we applied it to insider threat. What is insider threat? So there are bad people that are pretending to be good people. It could be people, or it could be processes in the system, right? So insider threat is very difficult because you all, looking at the process, it's looking like a perfect process, or outside it's looking like a perfect person. But, there could be some, but they are really bad. And so we have designed and developed an ensemble-based stream mining algorithm based on supervised learning that address this challenge by maintaining evolving collection of multiple models to classify dynamic data streams, okay? So the result is a classifier that exhibits substantially increased classification accuracy for real insider threat stream related to traditional, so we do supervised learning, support vector machine, and then we have also done unsupervised learning using a graph-based anomaly detection algorithm. In unsupervised learning, I'm sort of rushing a little bit because I want to leave because it's now 5:53 US time. So I started around 5:20, so about 30 minutes. So I've got about 20 minutes left, I think. Okay, so unsupervised learning, compression-based techniques are used because you want to make it more manageable. The results in a classifier exhibiting a substantial increase in classification accuracy. Our challenge is to represent the massive amounts of knowledge extracts as knowledge graphs, okay, amounts of knowledge extracted, as knowledge graphs, and conducted analysis to detect the insider, okay, and conduct analysis. Okay, so here is the architecture. So here is the person pretending to be a good person. There's a process. So we have various patterns that we can look at. Supervised, we have better idea. Unsupervised, we do all this compression and do some guessing game here. And so we have I chunks coming in, and then we gather all the data, all knowledge and data and so on. Ensemble of models, feature extraction is really the challenge, right? Because we need the domain expert to extract the features, because the domain cybersecurity expert, because the machine learning person is not really may not be a cybersecurity expert. So the cybersecurity expert, right, will extract the features, help us to extract the features. And then ensemble of models, learning algorithm, either supervised or unsupervised. And then once you learn, then the I+1 chunk will come in, extract features. And then you do the testing, is it anomaly or not, okay? So we got some very interesting results. And so it's published in a number of papers. I've listed in one of the papers. And so between the two, support vector machine and the GBAD algorithms, the graph-based, they've got their advantages and disadvantages, right? Typically with supervised versus unsupervised. And so unsupervised gave us a very good performance. This results in a classification exhibiting a substantial increase in classification accuracy. So that's something we found with the unsupervised algorithms. Okay. So now in the previous charts, I talked about the second point, right? Applying big knowledge, right, for cybersecurity applications. And that application was what? Insider threat detection. I only gave you one application. Now, the third, so first I talked about privacy, policy-aware privacy. That's one aspect we need to take care of for Secure HACE. Another thing is big knowledge for cybersecurity. third, which is really crucial, is that the big knowledge, the big data processing framework or big knowledge processing framework could be attacked. So if all those activities, data collection, data analytics, if they are attacked, what is the point, right? The whole system will collapse. So that's come to be called adversarial machine learning, because we've got to figure out what is the adversary doing. Adversary has to figure out what are we doing. So adversary modifies data to defeat the learning algorithms. Okay, so I'll explain to you with the example here. Understanding adversarial machine learning. It's not concept drift. It's not streaming data coming in and the concepts are changing. No, it's not about online learning, not machine learning. Adversary adapts to avoid being detected. It could happen during training time, such as data knowledge poisoning, or during testing time, such as modifying features when knowledge mining is deployed. And we play a game between us and the adversary. So who wins the game? So here you see the red squares are the bad instances and the blue circles are the good instances. And this is the support vector machine boundary line. See what happens. The adversary has learned what we are doing, our data and our models. And so it's now going to try to thwart it. How is it going to thwart it? There. The red squares are now coming as good instances, but they are really bad, right? Because they have learned what we are doing and trying to push something here. So now we've got to handle the adversary. So in reality, I'm not going to go through too much. Our KDD paper talks about it. In the next chart, I'll talk about our paper. So it's got the free range attacks, right? Adversary can move malicious data anywhere in this domain. And then others are targeted attacks. So the challenge we have, we are only looking at 2 types of attacks. In reality, there are hundreds of attacks. All the adversary is doing has to come in through one loophole. We've got to handle everything, which is impossible. And so some people criticize, so your work, right, trustworthy machine learning or adversarial machine learning, whatever, it's no use because adversary can always find a loophole and get in. So my answer is that something is better than nothing, right? So challenge, how do we apply the model for attacks on big knowledge? Okay, so look what happens. We move, the support vector machine line is moved here. So now you have the blue line that has been pushed, okay? So the green circles are the good instances, the red crosses are the bad instances. By moving this line, some of the bad instances are, we catch some of the bad instances. Otherwise, if the line is here, we won't catch those instances. See, there are lots of bad instances that we have caught. And some, of course, we don't, because a black dashed line is a standard support vector machine classification boundary. Blue line is the adversarial support vector machine classification boundary. And we have moved the blue line. Yes, you can move the blue line right here, then we could have caught all the bad guys. But when we do that, some of the good instances will turn out, like I said, they are bad instances. So we get some false positives. We don't want false positives and false negatives, okay? So some of the details are in our paper. So we have a lot of mathematical computations, and the whole challenge is to move this line at an appropriate place so that at least as quite a few of the bad instances would be caught. So that is a challenge. How far do you move the line, right? That is the research. Okay. Another thing that is very near and dear to me, and something that we need to do for knowledge graphs, we have done this for relational data, we've done this for RDF data, and that's called the inference problem, where you put collections of data together and infer something that is highly private. So we did this with RDF, right? So we have all of the policies, rules, and so on. You can represent them in knowledge graphs. We have an inference engine that is really doing some reasoning, like automated reasoning, rule processor. A pellet was developed at University of Maryland, College Park. And these are the technologies that we provide. And then we have a knowledge graph engine, right? So we used actually Jenna, which was RDF engine. And then we have knowledge graph documents. So you query and get all the results. The inference engine will take all the queries and then take the results and do some reasoning. and make a determination. Should I give these results to the user or not? Can he or she infer something that is highly private or highly sensitive? Okay, so that's another aspect that we have to focus on. Okay, so this is something that I'm really, I've done a lot of work in this area, as I said, since 1985, and I would still like to explore this now for knowledge graphs. Another thing, the last part in this particular part 2 I wanted to talk about is, remember, information sharing. That's the big data processing framework for Haze, right? Data collection, data access, data mining, and data sharing. And so what we did was we had multiple agencies between United States, Europe, London, and Italy, Como, Italy. So we built this whole information processing layer in the cloud, information sharing. Now we may want to, so it was all based on semantic web and RDF data. And so there are multiple agencies, but we can also apply this to autonomous vehicles. That's going to be my next topic, right? Different vehicles are different agencies, transportation agency, or we are pretending like it's Dallas, London, and in Subria, right? Different countries, but like we are different agencies, but actually we are universities. So autonomous vehicles or transportation agencies, Homeland Security, they could all share data. So what we do is we built a secure cloud and we put all our data and policies in the cloud. Okay, so all our data and policies in the cloud. And so when agency 1 wants information from agency 2, agency 2 says, okay, I can give it to you provided you don't share it with agency 3, right? These are our TOY policies. So we demonstrated this and we used, remember, this implementation, we re-implemented this, the policy manager in the cloud. And our cloud essentially is a MapReduce framework. We had the Hadoop HDFS is what we used, the Hadoop distributed file system. Today we might use Spark if you were to re-implement this with knowledge graphs. And so this is something, remember the information sharing, this is our framework for assured means secure and private information sharing. I call it knowledge sharing because we are not only sharing information, not data, information, but we are also extracting knowledge with the help of the domain expert. Okay, so these are the various pieces that need to be investigated for a big data, secure big data processing framework towards developing secure Haze. Okay, now we go to part 3 very quickly. I've got about 10 minutes left. Okay, secure Haze for Internet of Transportation and Critical Infrastructures. Gosh, Internet of Things, right? Wherever we go, whether we are refrigerator connected to your television, connected to your lights, and connected to your oven, and connected to almost everything, right? So that's Internet of Things. Internet of Transportation is a type of Internet of Things. All the cars are connected to the trains, to the roadworks, to the trucks. Everything is connected. Imagine the amount of data being collected. Okay, Internet of Transportation. IoT has major applications in the transportation industry. Autonomous vehicles aim at improving day-to-day activities such as delivering packages, improving traffic, and so on. 63.3% of the freight goods are carried by trucks. AVs are not limited to ground. We have also done work on aerial, like drones. We have not done work on any ships, sea vehicles. Wide range of applications. Usually they have come up with levels of automation for AVs going from 0 to 5. 0 is no automation, 5 is superb automation. But ground vehicles, still the cars, automation is only at level 2, whereas aerial vehicles, it's at level 4. Companies are investing heavily. 2008, GM spent 728 million, and 2009, they were hoping to spend 1 billion, and we need to get those results. While there's great potential in AVs and the improvements it can do to the transportation industry, of course, we need security and privacy, right? That poses new challenges. So essentially what I'm trying to say is that bring that big data processing framework of Haze into this application environment. Okay, so secure Haze for transportation security. Internet of Transportation systems are subject to attack, like any cyber-physical system, streaming data, lots and lots of data. So it does become big data, right? Autonomous, and in the future, we will have driverless vehicles. Such data combined with analytics and context could become big knowledge. Threats to the security, such as systems could have caused massive damage, accidents, losses, and stranded in lonely highways. Remember, energy management, soon we could even have, we already have electric vehicles and driverless vehicles. So data science, ML techniques being applied to analyze data. How can big knowledge management and analytics be applied to streaming transportation data? Okay, the main question is to understand the nature of this complex, evolving transportation data, right? And adapt stream analytics to big knowledge management and big knowledge management techniques for such data. And that research is only beginning. So our current work, and is published in Usenet Security, Raul Quenones and Alvaro Cardenas, and I am, as I said, I'm a co-advisor. So AVs evaluate their environment using variety of sensors like LIDARs and inertial measurement units and GPSs and cameras, but the sensors are susceptible to malicious tampering. IMUs are susceptible to sound waves, right? Attacks, and GPS receptors are susceptible to spoofing signals. So vehicles should verify the veracity of the sensor signals before acting. So we have developed a physics-based, we're not applied any big knowledge or big data or anything like that. It's complex, but the idea is simple, physics-based solution. We look at all the physical properties like the weight, the accelerometer, and so on, and look at all the Newton's laws of motion, right, are being applied, physics-based. And that's where Haze would be very interesting, since we are comparing it to Newton's laws. And that's why I chose this particular application. So we build a model offline on the AV's physical invariance. Our paper here, Usenet Security, talks about all the physics-based properties. Then we implement an online tool to monitor, and we use Kalman filter for the implementation, for the monitoring. Now, Kalman filter has been around, and we haven't used machine learning here, but machine learning is a possibility for the future. And we raise an alarm if significant residual difference exists. So how can we apply? The challenge is, how do we apply big knowledge management techniques? So offline pre-processing, building the model, online verification, and detecting the anomalies. So that's our approach. And then we implemented the physical implementation, aerial AV, Intel ready-to-fly drones, and then we had flight controllers focused on detecting GPS spoofing and gyroscope attacks. And you can see attacks detected after 0.2 seconds, and gyroscope attacks 1.5, overhead introduced 5.4332, ground AV custom built on top of Traxxas Ford Fiesta, and controller KOS Kinetic came, focused on detecting visual attacks on the camera, attacks detected after 0.1 seconds. The overhead introduced is 2.2501%. Okay, so here the overhead is slightly more, overhead is less. Each threshold produces a probability of false alarms of approximately 2%. Okay, so we have implemented this. Now we need to extend this to our environment, which is the big data processing framework. Of course, privacy, as I mentioned, beyond the security of individual vehicles, the transportation sector could greatly benefit from a supporting infrastructure that allows the communication between vehicles, motion sensors, lampposts, and so on. From the user's perspective, privacy concerns arise from all in the information needed by such systems that could lead to private information being exposed, such as vehicle identification and driving patterns. Okay, so all the information is being collected about us, right? So they could say, who is the driver? He has got all these bad driving patterns, and where is his location? So all that we don't want we may not want others to find out. So legislatures, engineers, and scientists should keep privacy concerns in mind as advances in IoT become more prominent in day-to-day activities. This will aid in improving the public perception, reduce hesitation from customers, and so on, right? Big knowledge for enhancing privacy, or big knowledge could also cause some privacy concerns. So those are some of the things that we need to investigate for this particular application in order to bring in Secure HACE into this. Okay, attacks to knowledge graph. So now I'm going to sort of apply some of the Secure HACE stuff I mentioned in the previous part 2 to here, because Internet of Transportation systems will be relying on big knowledge and analytics, right? So it could have driving without a human in the loop. So adversary will be learning the models used by us, okay, by the vehicles, as well as learn about the data knowledge. Adversary is going to thwart us, the vehicles, and we are trying to find out what the adversary is up to. So our learning algorithms have to adapt. Eventually it becomes gameplay between us and the adversary. What sort of game? Zero-sum game, Bayesian game. There's also Stackelberg games. Research is only beginning in this topic. Remember I mentioned about our smartphone, policy-aware, privacy-based knowledge framework. Remember, we have a big data processing framework. And then I talked about that framework. That's the framework that Dr. Xingdong Wu talked about. I talked about that framework if you want to develop a secure haze with respect to privacy. Now we can apply that, okay, in this environment, in a car. Instead of our smartphone, now we have our car. And instead of healthcare and fitness data, we collect radar, GPS, cameras, LIDAR, ultrasonic sensors. We have sensor, we have data collection, data storage, data analytics, and data sharing, and some of the data in the cloud and private. So how can we develop a privacy-aware autonomous vehicle? I talked about privacy-aware smartphones, right? Data framework. Similarly, we have a privacy-aware data management or knowledge management framework for this vehicle. That is our challenge. We haven't done that. I'm just throwing this. Okay, my last chart, only one more chart. And time-wise, I think we are doing quite well. I probably will have, I don't know, I haven't sort of kept time. I think I probably have a few more minutes to talk about, and then I think I will have some time for questions, summary and directions, just one chart. Developments in Haze and big knowledge graphs can be applied to numerous applications. Okay, so we said applications include cybersecurity, insider threat detection, security for knowledge graphs, adversarial machine learning. Also developments in privacy-aware healthcare and managing one's life's activities. Privacy-aware, sorry, it's a spelling error, quantified, Quantified, quantified self. At the same time, with the development of the Internet of Things, including Internet of Transportation, security and privacy solutions are being developed, mainly physics-based solutions, right? As driverless cars become a reality, more and more of the AVs will need big knowledge techniques. Yes, ACE. But we need to secure those techniques. So how can we develop solutions on knowledge graphs for detecting malware in AV systems? How can adversarial ML work in AV systems? So what I'm saying is, how can Secure Haze be applied to a secure autonomous vehicle, secure Internet of Transportation? Can we develop a privacy-aware, policy-based big knowledge framework for Internet of Transportation? And we have numerous opportunities for substantial research. And I'm going to come to my concluding remarks. Okay, I'd like to thank, as I said, my colleagues, Alvaro Cardenas, Murat Cantajalu, Latifa Khan, our former PhD student, Dr. Raul Quinones, and Ms. Rhonda Walls. Okay, so this ends my presentation, and I want to stop sharing so I can just give you some final thoughts and what I want to stress, right? So we had, let's see, first I talked about Haze, and that is the brilliant work of Dr. Xingdong Wu. Okay, so I believe just like Newton's laws were important, right? Remember I talked about as Internet of Transportation infrastructures, physics-based solutions, physics without Newton laws. That's a fundamental to physics. So our model there was based on Newton's laws. And so just like Newton's laws were important, critical for physics, right? We have Haze for big data. Great. And then Dr. Wu also talked about a big data, and his team, of course, several co-authors, they talked about big data processing frameworks. Now, then I said, how can we develop, my part 2, how can we develop a secure Haze? That means we need to incorporate security into that entire framework, security and privacy. I talked about different pieces, building blocks that we've got to put together, and maybe also several additional pieces. So I talked about the privacy-aware, quantified self, so privacy-aware, policy-based. Policies should guide data collection, data analysis, data sharing, data management, the whole lot. Then I talked about big data, big knowledge for cybersecurity applications, because lots of data are being collected and we have lots of attack data, right? So you need to apply big knowledge and machine learning, data science, data mining to analyze the data and come up with those nuggets, right? Have there been attacks? So I gave an example, which was the insider threat detection. Okay, so that was, and then I said, these adversarial machine learning, all of our data collection, data analysis, data sharing, everything, all those activities could be thwarted by attacks. And so that, then I talked about adversarial machine learning, right? We've got to be one step ahead of the attacker. And attacker has, you know, a whole array of attacks, but we are only finding solutions for a limited number of attacks. But my premise is something is better than nothing. Then I talked a little bit, I believe, about the inference problem, where we can put, that's very dear to me, collections of data together and infer something that is highly private or highly classified. Then I talked about policy-based secure information, assured information, that means secure and private information sharing in the cloud. And I showed our demonstration system. So that was all the building blocks towards Secure Haze. Then my part 3 was like part 1 is, yeah, part 3 was on Internet of Transportation, right? I gave an example, physics-based solution, how we applied it to drones, aerial vehicles, and cars, right? Ground vehicles, and talked about what are some of the challenges. And I even talked about privacy aware. We haven't done that work yet. Privacy aware, policy-based autonomous vehicle, right? And so that there, remember the Secure Haze that we develop in part 2, well, we haven't developed it yet. I talked about the building blocks which have to be put together. That could be applied now for Internet of Transportation, okay? So that is one of the applications. And then my conclusion was, you know, how do you, and all the opportunities that we have for future research. Okay, so I think I may have a few more minutes for questions. So again, thank you so much for inviting me to give the keynote address. I wish I was there present to give this address, but unfortunately we've got this COVID-19, and so I could not attend. And hopefully next year we can all get together and you know, and talk about some of the challenges. Maybe we would have solved some of the problems to achieving Secure Haze. Again, thank you very much, and I'm here for questions. Thank you. So I'm going to stop the recording.